Okay, so I'm just going to give it maybe 1 minute more or so, because there's usually at least 2 more of us. So I'll give anybody a chance whose clock's not set exactly the same as mine. Don't forget that the one behind my head is set 5 minutes fast, so that I never miss the train. So if you want to know what the time is at any point, look at your computer clock, not mine. So we're really nearly there with this semester. Got just this week to go, and then it's over. So I hope it's not been too stressful. I feel like the last few weeks of this course are a repetition of the same type of thing, and that's a little bit reassuring, that you can feel like if you can get your head around what this hypothesis testing stuff is about, that you can feel confident about this course. So, as I mentioned before, we're going to do question number 2, which is very similar to one of the questions we did last week. So it'll feel a little bit like we've been there before. We're also going to do question 3. Again, also quite similar to what we were doing last week. And possibly question 5 if we get time. What we're going to see, the reason why I've picked those 3 is because we get to see how our assumptions affect what we want to be doing in each case. So without further ado, let's get on with it. Okay, so let's just check this is in focus. It's not quite. That's better. Okay, so in question 2, we had 2 types of car tires. And our statistic was showing the thing that we were measuring was the wear in millimeters. And for type A, we had a sample of size 25. We had a mean wear that we observed from the sample of 10.24, and we had an observed standard deviation as well. Oh, no, we didn't. No, we didn't. I'm jumping ahead of myself and thinking about the next question. For type B, we also had 25 observations, and we had an observed mean of 9.76. And we were allowed to assume normally distributed. And we were given the variance. So we were given that for tire A, we had a normal distribution with an unknown mean, so mu1 that we don't know what it is, and the variance was given as 1.742. And for tire type B, again, normal distribution, unknown mean, mu2, and the same variance, 1.742. And in the first part of the question, we were asked to test the hypothesis that the 2 means are equal. So the test that we want to do, the null hypothesis that we would like, is that the 2 means are equal. And the H1 hypothesis I'm going to use is that they're not equal. Okay. So I'm at this kind of stage. I was told that I want to do the test at the 5% significance level, so I want to set alpha is equal to 0.05. The key question there is, what kind of test statistic do I want to use? And when do I reject the null hypothesis? Okay. Get a bit more in focus for you there. That's much better. Okay. So I'll just give you a couple of minutes to think about that or check what you've done for that. I'm hoping that it's very much related to what we were doing last week. So I'm going to call my test statistic Z. Maybe if you can remember it, write down what the formula is for it. Also have a think about when you're going to be rejecting the H0 hypothesis. So the first thing we should be thinking about is how we're going to estimate the difference between the two mu's, given the data that we've got. So we've got the means from the two samples that we're studying. So the best we can do is to take the difference between. So somebody's asked, how do we know which conditions to use for H0 and H1? It's a really good question. So it's from the wording of the question. So the wording of the question asked us to find out whether they had different mean wears in millimeters. So the key thing there is the phrase difference. Which is making me think, oh, I'm going to have to take, yeah, I'm going to have to take the difference between the estimated means. I said the sample means, also, phrasing also said is not the same, or is not zero, rather than bigger or smaller, which is what gave me the idea of that, that should be the H1 hypothesis. So if you're not given what H0 and H1 are, read the question and interpret. It's the same as what these values are. Sometimes they're put there in a very nice format for you to just use immediately. And sometimes they're embedded in the text. So it's just a case of interpretation. And that's one of the, more tricky things about questions on some of your courses, I'm sure. Yeah, so the first thing I'm going to do is I'm going to put in my estimate for the difference between the two means, which is just going to be the difference between these two. And I'm going to standardize this. This is, the general thing that I was doing is standardizing my random variables so that they're normal 0, 1. Okay. So how am I going to normalize it? Well, I've been given what the variance is, so I don't need to use an estimate for the variance. I can use the number that I've been given. So I'm going to use this guy with the known variance in there for sigma, so there's no estimate for the sigmas. And if H0 is true, so if my null hypothesis is true, this random variable here is normally distributed with parameters 0 and 1 if H0 is true. So we can reject H0 with 5% confidence if the absolute value of Z is in the tails of the normal distribution. So it's bigger than 1.96, which, if we remember, is little z 0.975. So that's what's going on there. And if you calculate what the test statistic is using the values in the question, so you plug in all of the values that you get here, we get a value of z to be 1.286, which is less than the threshold I'm looking at, less than 1.96, which implies we can't reject H0. Or there's no evidence to suggest the where is different. Okay, so Cameron's asking why do we use Z 0.975, and that's because we've used a 5% confidence level. So because we're going for not equal to, we want to be having a 5% chance of rejecting Z, and we're going to reject it if it's very, very small or if it's very, very big. So if I'm thinking about what the normal distribution is looking like, a 5% chance of rejecting H0 when H0 is actually true. So if we think about if H0 is true, then Z is normally distributed with parameters 0 and 1. So I've got 0 here, and I've got a 2% chance, 2.5% chance that Z is in either of those two tails, where this value here is minus Z on alpha divided by 2, and this one here is Z1 minus alpha divided by 2. Is that kind of clear, Cameron? Is that good? And again, I've not noticed that when somebody's been direct messaging me, so I'm really sorry for shouting out your name there, but it was a really good question, and I'm sure lots of other people were thinking exactly the same thing. Okay, right. So I've crammed that in a little bit there, but hopefully that's good. All right. So following on from what Cameron was saying, with question 2, before I crack on to actually doing the calculation, I wanted to show you a little table to sort of show what we're looking for. Now, we've got 2 possibilities with the hypotheses. We've got H0 is true, and we've got the possibility that H1 is true. Now, neither of these we can observe, so we're not too sure which of these is actually the case, but certainly reality says that either one of those 2 is actually the case. And then when I look at my sample, I've got 2 possibilities. I either observe that the absolute value of Z is bigger than 1.96, or I observe that the absolute value of Z is less than 1.96. Okay. Now, if H0 is a true statement, I've got a 5% chance of this one happening. Now, this one is I actually reject the H0, but H0 is true. So that's not a situation I would like to be in. That's a bad situation. I've accidentally rejected my hypothesis, even though it was actually true. I've got whereas if I observe that the absolute value of z is less than 1.96, I've got a 95% chance of that happening. This is a good situation. I'm drawing the correct conclusion in this situation. So this one's a correct conclusion. Now, if H1 is true, I've also got a correct conclusion and a false conclusion. So, and I'm looking for in part B the probability that goes here. So I'm looking for this value. So I'm looking for the probability that I observe that the absolute value of z is less than 1.96, but H1 is actually true. And in this case, I've specified, it's been specified what exactly is wrong with it. So H1 minus H2 equals 1 is what has been proposed as the actual truth. So I want to find out what's the probability that I make an observation that means that I don't reject H0, but that H1 was actually the correct thing. So we need to find this one here, which is an incorrect conclusion again. Okay, so how do we do this? Now, the first thing to do is to think about the region on which H0 is rejected. So I'm going to give it the curly brackets because I'm going to think about it as a set, which I can later take the probability of. And I've just stated in the first part of the question that we've got the absolute value of z is less than 1.96. So how can I write this in terms of the x's so that I can re-standardize it? So the first thing I want to be thinking about is, okay, let's go for the absolute value of z1 minus, so x1 minus x2 bar is going to be less than 1.96, and then I'm going to have to multiply by the factor that I was using to divide, but to standardize by. Okay, great stuff. And I can actually calculate what this factor is because I know what those values are. And when I kind of put all of that together, this number here is 0.3733. So I can use that. Okay. So now I want to re-standardize with the correct mean. Correct difference between the mean. So the correct value of mu1 minus mu2. Which the question said was 1. Okay. So where I'm going to end up is in a situation like this. Yeah, I think I would maybe prefer not to write it like this. Okay. So I'm sort of better switching to two inequalities rather than using the absolute value, because that helps with making sure that that nothing goes wrong there. So I've taken off what the actual value of the difference between the two mu's is. I've got this expression. And now I know that under that actually this random variable in the middle is normally distributed with parameters 0, 1, 1. So I'm going to define it equal to some value y, which is normally distributed with parameters 0, 1, 1. This one. So I couldn't go directly to this before because I didn't know what the difference between mu1 and mu2 actually was. So if the difference between mu1 and mu2 is 1, then y is normally distributed with parameters 0 and 1. And then I can use this expression for the rejection region that I've got to calculate the probability that H0 is rejected. So what's the probability of this event here? So I'm looking for this guy. So the probability that the absolute value of y is less than 1.96 minus this one. Oh, no. I keep jumping into this one, which is not right. Okay, minus 1.9. Okay, so what's the probability of this guy? And I know I can find the probability of this guy in terms of the CDF of the normal distribution, which I can look up in the tables because I've standardized it so that y is normal 0, 1. And I end up with this guy, which if I look up in the table is going to give me 0.24. So what I've got is I've got a 24% chance that I observe a value of z. So let's go back to my table here. I've got a probability of 24%, 0.24, 24% here, that I observe a value of z that's less than the threshold, so less than 1.96. So I reject. So I'm not allowed to reject H0. So the data I've got is suggesting that I can't get rid of the null hypothesis, but the reality is that the difference is 1. So that's not great compared with the fact that I've only got a 5% probability of rejecting H0 when H0 is actually true. So what I wanted to stress with the little table is that certainly with the H0 hypothesis, whether we reject it, we incorrectly reject it or not is determined by, completely determined by the parameter alpha that we set, so the confidence level that we set. If we've got a true alternative hypothesis, first of all, the probability that we accidentally don't reject, so we draw an incorrect conclusion. We draw the conclusion that we can't reject H0 even though H1 is true. First of all, that depends on the value of the actual difference, and secondly, it's not exactly the same as the confidence interval. It does depend on the confidence interval, but kind of in an indirect kind of way via the 1.96 there. Okay, so hopefully you found that helpful. Fingers crossed you found that helpful. So why don't we take a look at question 3 and let's try our best to do it together. So in question 3, we were given 2 different drugs, A and B. And we were given some sample sizes, some means, and some observed variances. Okay, so some sample variances. Okay. We're allowed to assume that the response times are normally distributed again. We've got alpha equals to 0.05 again, so 5% confidence. So we're allowed to assume normal distribution. Now, in the first part, we were asked to test whether the mean absorption times were the same. When assuming that the values of the 2 variances are different. Oh, completely can't see that. Hayden says, please move your notebook down. Nobody can see what you're doing. Great. She's completely right. So, so thankfully, all I've written is stuff that was already on the question. So the first part is test if the 2 means are the same when assuming that the variances are different. So I'd like you to think about the same things again. What test stat am I going to use? What hypothesis? And when do I reject? Okay. So I'll just give you a couple of moments to think about those, maybe 1 or 2 minutes, and then we'll come back and run through them. And then once we're sure that we've all got the right ones, I'll give you another couple of moments to to do the test and to draw a conclusion. Okay, so let's start off with the middle one. So what hypothesis? I think that one was stated in the question, that we're going to use the null hypothesis that they're the same. And a H1 hypothesis that they're different. Okay, so what test stat am I going to use? I'm going to do pretty much the same as I did last time, but this time I don't know what the variance is, so I can't add in the variance directly. I've got to put an estimate instead. So the first thing on my test stat is going to be an estimate for what the difference between the two means is. So x bar 1 minus x2. And then I'm going to want to divide that by a standardizing factor. So this is going to be, now before I had sigma squared in there because I knew what the joint variance is. Here, first of all, I don't know that I can't assume they're the same value, and I don't know what either of them are either. So instead, I'm going to use S. I've got S1 squared divided by N1 plus S2 squared divided by N2 on the bottom there. And I know that if H0 is true, this random variable is going to be, so this is distributed normal 0, 1 if H0 is true. And when am I going to reject H0? Hopefully you can see that because it's a not equals here, I'm going to have to use the absolute value of Z as something that I'm going to be looking at. So absolute value of Z needs to be bigger than little z 0.975. And the parameter here is exactly the same as before. Because we've gone for two-sided, I need to use 1 minus alpha divided by 2 as the value there. Okay. So that sort of got me, hopefully got us going. So see what you can do. See if you can just quickly plug in the values of the S's, the N's and the X's to get this test stat, and see if you can draw a conclusion. And I'll just give you a couple of minutes to give that a go, to give drawing a conclusion again. And then we'll come back and have a little chat about what we're going to have to change for part 2, and you can have a go at that part as well. Okay, so if you got your calculator out, you would have seen that we have observed a value of Z of minus 2.49. So what we've got here that's a little bit tricky is we've got a really, really small value of Z. So we're going to have to be a little bit careful with what's going on here. So when we take the absolute value of this, we get 2.949. So something quite big. It's bigger than 0.96, so we can reject. So hopefully your conclusion was we reject H0. We've got evidence to suggest that the means are not equal under ours, under this assumption that we've assumed that we don't know the two values of the sigmas, but that they're definitely not equal. So what happens if we change this assumption here, that the two means are equal? So the variance remains unknown, but we assume that it's a common variance between the two samples. So what do we need to change? So I think the first thing that looks like we're going to need to change is something in the test statistic, because we can do a bit better than putting S1 squared and S2 squared in here. So So the first thing we want to do is estimate a common variance, sigma hat squared, using sigma hat squared using S1 squared and S2 squared. And then the second thing we want to do is to change our test stat. And then have a think about what is the distribution of your test statistic going to be under the H0 hypothesis. Okay, so have a think about those three. I'm going to give you a bit longer to have a think about that, maybe verging on 5 minutes. We'll come back about, well, with a minute or so to spare in the class, and just talk about what you need to change and hopefully prompt you in the right direction to be able to finish things off. So yeah, have a little think about those three questions. If you're not clear about what you need to be doing, or you've got any questions, feel free to ask me or Hayden. Feel free to talk to each other about it, of course. I'll try my best to give you some quiet time to work. Okay, so somebody's asked me, how did I calculate Z in the previous part? So to calculate my Z, I just put in the values from the question into my test statistic, this one. So I think what is a little bit confusing on why I've left it as a capital Z, even though it's an observed value from that particular sample, is because we've got a little z here for the threshold, and I don't want to confuse myself too much. But how I calculated the observed z, this minus 2.49, was I took the values from the question, so x bar 1, x bar 2, from the question. And also S1 squared, S2 squared, and the sample sizes from the question, stuck them all in, kind of cranked the handle with my calculator, and did my best to get 2.49 out. No, I like all of these questions. You know, I think they're all really, really good because it just, you know, often it feels like a little bit of a wall of text. And I want to be sort of adding something from the solutions that Sarah Lees is issuing because, you know, clearly all of the numbers and things are there. So hopefully a little bit of commentary to sort of guide you through is the value that these classes are even adding, because otherwise you could just stay away and just read the solutions, which, you know, I hope I'm better than reading the solutions is what I'm trying to say. So I'll just move that back up again so you can see what we do. So the first one of these, estimating the common variance, the key thing I needed to do is to remember the formula for it, which is this one. Okay. So if you plug the numbers in, you should be in the realm of 17.715. Right. So the next thing I asked was, how's this going to affect your test stat? So if you look back at the previous test stat, I had S1 and S2 in there. I don't want those in there anymore. I want to be using this common variance, which is going to be more accurate. So I'm going to change the name of it as well, and it's going to give you a little bit of a hint for the final part. So I'm going to call it T now. And I'm going to go for x1 bar minus x2 bar, and then what I'm going to be standardizing by is a factor where I'm going to put that estimate for the common variance in. That's right. Okay, so the test stat T gives you maybe a little bit of a hint as to what I was looking for at the final part there. So what's the distribution of the test stat under H0? So T is going to have a student T distribution. With how many degrees of freedom? Now that's the tricky bit, is I have to look at the sum of N1 minus N1 and N2 as the degrees of freedom then. And also subtract off 2. Okay. And then the final thing I'm going to have some difficulty with is finding the rejection region in that case because of the large degrees of freedom. If you look at the table that Sarah Lees has given you in your formula sheets, it doesn't have a row for 48 degrees of freedom. So it's 68 degrees of freedom, so you have to decide what you're going to do with that. And what you should be doing at that is looking at the row below that is available. So the nearest one that is smaller is 60 degrees of freedom. So use the 60 degrees of freedom row. And hopefully that is enough to get you sort of started and pointed in the right direction to finish off that second part of question 3. Okay, so we're finished. Sorry I didn't get a chance to try and cram in question 5 as well. Yeah, I don't really have anything else to add other than best of luck with your exams, all of them, including this one, in particular this one. And if you have any questions between then and now and then, feel free to get in touch with Sarah Lees. I know he's given you loads of ways of getting in touch with him, you know, whenever you might find that convenient. You can always ask me as well, but you might want to ask Sarah Lees, you know, because he's the man in the know. He's also the man who set the exam, so and has set the exam for a number of years. So he's sort of much more aware of, you know, what he wants you to be able to do and what standard you need to reach to get a good grade in this course. So without further ado, best of luck, and I hope I get round to teaching you in a further year.
Hello, good morning, guys. How are you? Guys, good morning, everybody. Hope you are well. Oh man, what's happening? Okay, right. I'll start in a second. Just a reminder that the R coursework is due on Thursday. There's 2 days time. So if you haven't submitted, please do so as soon as you can. Okay. All right. So let's begin. So this is tutorial for week 12. So we are going to look at sheet 12. So let me show you if you haven't seen it. This is sheet 12. As you can see, just a minute. There are 5 questions. There are 5 questions in sheet 12, and I will try to do as many as I can. And as I go along, all the questions you guys have, please use the chat room. I'm more than happy to answer all your questions. So let's start with question 1. Okay. So here you have 2 different type A and type B stops, right? And you're trying to compare their means. So you're told that the numbers for the 2 types, you're given the sample means for the 2 types, and you're trying to compare the mean boiling times, and you're told that the population variances are this and this. And the question is to test this hypothesis versus this hypothesis at the 5% level of significance. Right? Now, to do this kind of stuff, I mean, sheet 12 is all about 2 sample test of hypothesis, right? So I don't know whether you recall what we did about 2 weeks ago. Let me just take you through what we did 2 weeks ago. 2 weeks ago, I gave you the rejection rules for testing for 2 sample problems. The first problem I considered is you have 2 different independent samples, and you're assuming that the population variances, this and this, are known. In this case, these are the 3 different hypotheses, and these are the rejection rules, right? So that's the first case I considered about 2 weeks ago. The second case I considered is this one, where you have 2 independent random samples from normal, but here the variances are common, they are equal and unknown. And in this case, the rejection rules are this one, and this one. All right. Now, the third case I considered 2 weeks ago was the most general case. Here you have 2 independent normal random samples, and the population variances are both assumed to be unknown, right? Okay, and in this case, the rejection rules are this, and this, right? All right. And finally, the final case I considered was this, where you have 2 independent Bernoulli populations. These are the population proportions. They're assumed to be unknown. And in this case, the rejection rules are this, and this, right? All right, now let's get back to the question. Let's get back to question 1. So here in this question, we are assuming that the population variances are equal, are known. I mean, so this is for the first population, this is for the second population. So this question corresponds to case 1, right? We are assuming that the population variances are known. Now we are trying to test whether mu1 equal to mu2 versus mu1 greater than mu2. So if you go back to this formula sheet, that corresponds to this rule here, right? And the corresponding rejection rule is this one. So this is the rejection rule I'm going to use in order to answer part 1 of question 1. Is that clear, guys? I mean, the first thing, I mean, for any question on test of hypothesis, you should figure out what is the rejection rule to use, which one is the correct one to use, right? And because if you get that part wrong, then you will get no credit for the answers that you give, right? Okay, so the rejection rule for part 1 of question 1 is as follows, as I just described. Okay. Okay, this is the rejection rule, right? And let me put this in a box. Okay. Right. Now what I'm going to do is I'm going to compute the left and the right hand sides, the left and the right hand side of the rejection rule, and then see if it is satisfied or not, this inequality. Before I do that, let me write down what is given to us. We are told that x bar is 11.4, y bar is 9.9. We are told that m is 10, n is 12. We are told that sigma x squared is 6.25, and sigma y squared is 9. And furthermore, we are told that alpha, the level of significance, is 5%, which is 0.05. Okay, so these are all the data that's given to us, right? So let's look at the left-hand side. The left-hand side of star, you should just sub in these numbers into the left-hand side. This is what you will get. Okay, now using a calculator, you can work this out to be 1.279. Okay, so this is the left-hand side number, right? The right-hand side of star is Z1 minus alpha. Yeah. Now alpha is 0.05, so this is Z 0.95. And if you read this off the table, for the normal distribution, this will be 1.645. All right, guys, so this is the left, this is the right. Clearly, this is not greater than 1.645. So the conclusion is that we cannot reject the null hypothesis. So what you write is the following, that you say there is no evidence against the null hypothesis. All right, guys, is that clear or no? Hello, guys, talk to me. Right. If it's not clear, please feel free to say so. I'm happy to go over. Are you okay, guys, so far? Hello. Are you guys okay? Yeah, thank you. Thank you, Harry. All right, so that's the first part of question 1. The second part of question 1 is asking you, what is the probability that the test will correctly reject H0 if μ1 minus μ2 is equal to 2? So let's see how we can do this. So this is question 1, part 2. So we are looking for the probability that of rejecting the null hypothesis when the difference between the population means is equal to 2. All right, guys, so I'm going to show you how to do this because I think all right, to do this, first you need to figure out the rule. I mean, the rule I have already written down here. This is the rule for rejecting the null hypothesis, right? So what you have here is the probability that is greater than z1 minus alpha given mu1 minus mu2 is equal to 2, right? You guys with me? All right. Now, the next line, I'm gonna sub in the numbers. We know from earlier that these are the values for the sigmas, and we also know the values for the m and the n. So if you sub in the numbers, this is what you will get is 6.25 divided by 10 and 9 divided by 12. All right, so this is what you get. And the right hand side we saw earlier is 1.645. Okay, given that mu1 minus mu2 is equal to 2. All right, guys. Are you okay with me so far? All right. Now to compute this probability, I'm going to apply a trick. It's a similar trick I used earlier, you may recall. Now what I'm going to do is I'm going to subtract a 2 from this and add a 2. I will explain why I'm doing this in a sec. Okay. All right. Next, I'm going to take this term here, the third term, to the right-hand side of the inequality. So this becomes the probability that now let me ask you a question. You may recall, some of you may recall, you may remember this. What can you say about this? I mean, given that the difference between the population means is equal to 2, what can you say about this, guys? Do you remember or not? Hello. Do you remember the following result? I think I mentioned this earlier in one of the earlier tutorials. That if you have a random sample of size n1, which are IID from normal with parameters this, right? And if you have another random sample, say x21 to x2 n2, which are IID from another normal with parameters this, right? And if these two random samples are independent, suppose these are independent of each other, all right? All right, then the following result is known. I think I proved this. I proved this result in one of the videos I did. I think it's the video on the two sample confidence interval, if I remember correctly. So please, if you don't remember the proof of this, please have a look at it. Okay. So what it says is this. That this guy here as the standard normal distribution. Right, this is the proof I gave you some time ago. I mean, I don't expect you to know the proof for the exam, but it's good to know it, and I mean, it's good to remember this result anyway. All right, so this is, you guys remember this or not? No, I mean, this is something I proved earlier, right? So using this result, right? Okay, the distribution of this conditional on the, oh, sorry, I forgot to put something here. The distribution of this conditional on the difference in population mean equal to 2 must have the standard normal distribution, because what you have here is exactly of this form, right? So what you can say, right, is that this guy here, this probability, you can write as the probability that a standard normal variable is greater than okay, greater than this, okay, right? And again, we don't need the conditioning anymore because we have used the conditioning to argue that this has the standard normal distribution, right? Right, and this probability you can write it as 1 minus and if you read this off the table for the normal distribution, you will get this to be equal to 0.52. All right, so this is the probability of rejecting the null hypothesis when the difference in the population means is equal to 2. Okay, guys, are you okay with this? Hello, talk to me, guys. Are you okay with this second part of question 1? All right, thank you. All right, so let's go to the next question, which is, so we're done with question 1. Question 2 is this. So you have here 2 different types of tire, type A and type B, right? And the question says, these are the number of observations, and these are the sample means. And the question also says that the 2 different types have a normal distribution with common variance equal to 1.742. The first part is to test at the 5% significance level whether there is a difference in the mean tire for the 2 types A and B. All right, now in this question, again, that we are assuming that the variances are known. The variance for the 2 populations are known, but they are equal, right? So once again, the case that we need to use is this one here, is the case number 1, except that the variances sigma x squared and sigma y squared are assumed to be equal, right? And we are trying to test equality versus not equality. So the rule for rejection is this one, right? So I'm going to use this as the rejection rule, because as you can see from the wording of the question, the question says test whether there is a difference in the mean, which means equality versus not equality, right? All right. Okay, so let's begin. Question 2. This is question number 2, part 1, right? So first of all, I'm going to write down the rejection rule. So we're going to reject H0 if right? If this is the case, right? So let me put this in a box as usual, right? Right. Before I start, let me write down what is given to us in the question. We are told that m is equal to 25 and n is equal to 25, right? We are told that x bar is equal to 10.24, y bar is equal to 9.76, and we are told that sigma x squared and sigma y squared are equal and equal to 1.742. And we are also told that alpha is 5% or 0.05. All right. So this is all the data that's given to us, right? So given this data, we can compute the left and the right hand side. So starting with the left hand side, right? Let's see what happens. We're trying to see all right. So starting with the left hand side, it's gonna be x bar, which is 10.24, take away, 9.76, right, in absolute terms, divided by 1.742, 1.742, right? All right, now if you work this out using a calculator, this is what you will get. You will get 1.286. All right, this is the left-hand side. The right-hand side, now alpha is 0.05, so this is 0.975, right? And if you read this off the table, you will get this to be 1.96. All right, so this is the left and this is the right. Clearly the left is not greater than 1.96, right? So the conclusion, once again, is that you cannot reject the null hypothesis. So in other words, you write this as there is no evidence against the null hypothesis. All right, guys, is this clear to all of you now? Hello, guys. Talk to me if if it's not clear. I'm happy to go over again as many times as you want. I'm happy to go over. All right, are you okay with this, guys? Hello. All right. Okay. All right. So I take that as a yes. All right. So let's go back to question 2. So we've done the first part. The second part is what is the probability that the test will incorrectly fail to reject the null hypothesis if the true difference is equal to 1. So what this means, I mean, you should read the wording carefully. It says incorrectly fail to reject the null hypothesis, which is the same as saying accept the null hypothesis when the difference in means is equal to 1, right? So what we are looking for, is the following probability. So this is question number 2, part 2. We are looking for the probability of accepting the null hypothesis when the difference in the population means is equal to 1, right? Now remember, this is the rule for rejecting the null hypothesis, right? So the rule for accepting the null hypothesis will be the reverse of this rule, right? Okay, so So instead of greater than, you're gonna have less than or equal to. Yeah, you with me? All right, in the next step, I'm gonna sub in the numbers for this, right? We know from earlier that sigma x squared is 1.742 divided by m is 25, and sigma y squared is also this divided by 25. Right, and we also know that this guy here is 1.96. Yeah. All right, now these two numbers are the same, so you can say this is going to be 2 times this number, right, which is 1.742 divided by 25. Right. Okay, in the next line, what I'm going to do is I'm going to get rid of the absolute sign. I think I mentioned this before. I don't know whether you guys remember or not. If you have an inequality like this, right? This is the same as saying that do you guys remember this or not? I mean, this is something you should have learned in your math courses. But anyway, do you remember this or not? That is, if the absolute value of a number is less than or equal to a, then that's the same as saying that number must be between minus a and plus a, right? Okay. So I'm gonna use this fact to rewrite this, right? Okay. Okay. All right, guys, are you with me so far? All right, let me know if you're not. All right. The next thing I'm gonna do is I'm gonna, as I did in the previous question, right? Because the true difference between the population mean is equal to 1, right? I'm gonna do the following. You see what I've done? I have subtracted the true difference between the population means and added the same thing, right? Okay. All right. In the next step, I'm gonna take this third term here to either side of the inequalities, right? So this will become like this. On the left hand side, you will get this. Right, and right? And on the right hand side, you will get this, right? All right. Okay, guys. Are you with me? Okay. All right. Now I'm going to make the argument that this guy here, conditional on the difference between these two equal to 1, this must have the standard normal distribution. That's because of this result I mentioned a few minutes ago. Remember this result, that if you have these two independent random samples, then this has standard normal, right? So because of that, this conditional on this must have a standard normal, right? So that's what I'm going to say in the next line. All right. So once again, the conditioning is not needed because we have used the conditioning to argue that this has a standard normal. So it's no longer needed, right? All right. So finally, or not yet finally, but near there, right? This probability here can be written as the difference of these two probabilities. So phi at 1.96 take away this, right? And minus phi at minus 1.96 take away this. Okay. All right, guys, and if you compute this using the table or some other means, you will get the answer to be equal to 0.24. All right, are you okay with this question or not? Hello, guys, you've been quiet today. What's up? Are you okay now or not? Talk to me, guys, please. So we are done with question 2. Before I go to next question 3. All right. Yeah. Okay, Harry. Thank you, Harry. So let's move on to question number 3. So we're done with question 2 now. So question 3 is this one here. So you have two different drug A and drug B. And drug B is given to 33 people and drug B is given to, drug A is given to 33 people and drug B is given to 37 people, right? And if you go to the next page, it gives you the mean absorption. So these are the number of people the drugs are given to, and these are the sample means of the absorption time, and these are the sample variances of the absorption time under the two different drugs, right? So we're trying to test under the 5% significance level whether there is a difference in the mean times to absorption for the two drugs, right? And there are two parts. The first part is assuming that the variances are not equal. The second part is assuming that the variances are equal, right? All right, now in this question, you have to be careful because the question says explicitly that these are the sample variances, which means that the population variances are not known, right? I mean, if the question gives you the sample variances, that means automatically the population variances are not known. So in other words, going back to the formula sheet, you cannot use this case 1 because here we are assuming that the population variances are known, right? So this one cannot be used. So, and this one here, we are assuming that the population variances are equal. So this cannot be used either because for the first part, we are assuming they are not equal. And if you go to the next page, here we are assuming that the population variances are unknown and not equal. So this is the rule. So these are the rules that you need to use, one of these rules. Now, since in this question, we are trying to test whether there is a difference in the mean times or not, the rule that we need to use is this one. So it's equality versus not equality, right? So we need to use this rule for question number 3, part 1, right? Okay, so let's begin. So I mean, as I said, it's really important that you choose the correct rejection rule, right? Because if you end up choosing the incorrect rejection rule, then you will get no credit for your mark. Okay, so the rejection rule that is most appropriate for this question is this one. All right, this is the rejection rule, right? So once again, let me put this in a box, call this star, right? Now, before I compute what is given, let's write down what is given to us. All right, we are told that M is 33, N is 37, X bar is 28.2, Y bar is 30.7, X squared is 16.36, SY squared is 18.92, right? And finally, alpha is 0.05. So these are the data that is given to us, right? All right, so let's compute the left-hand side to start with. So I'm going to start with computing the left-hand side of star. So this is going to be 28.2, take away 30.7, divided by this, which is Sx squared is what, 16.36, divided by 33, 18.92, divided by n, which is 37. All right. Now, if you compute this using a calculator, you will get this to be 2.49. Okay. And the right-hand side of star, right, is gonna be is this guy here, right? Alpha is 5%, so this is 0.975. Now the problem with this percentile is that you should remember the expression for A is very complicated. I mean, in fact, you should remember this is the expression for A that I gave you about 2 weeks ago, which is really, really complicated. I mean, you can compute this, but it will take you ages to compute this. So if you can, so the thing is, if you can avoid using this, it's best to do that. Now, going back to the question. Now, if you look at this question here, the sample sizes are 33 and 37, right? Which are large, because I think I told you before that in statistics, anything above 25 is considered large. So 33 and 37 are certainly large sample sizes, right? So in that case, you can approximate this guy here by the normal percentile. All right. The reason for this is that these two numbers are greater than 25. Okay. Now this is very easy to read using the normal table. I'm sure you know. This is equal to 1.96. All right. So this is the right-hand side, and this is the left-hand side. And clearly, 2.49 is greater than 1.96. All right. So the conclusion is that there is evidence to reject the null hypothesis. All right. Are you guys okay with this or not? So I have used this approximation because the reason, the rationale behind this is because the expression for A is really, really complicated. So if you can avoid using that, that's a good thing, right? So I have used, in this case, because the sample sizes are large, we can approximate the T percentile by the Z percentile. I think I mentioned this before in the class, that the T distribution can be approximated by the Z when the sample size is large. Okay, so that's what I have done here. Okay, are you guys okay with this? All right, so that's only the first part of question 3. Now the second part of question 3 is asking you to assume that the variances are equal. So in this case, so this is question 3, part 2. In this case, going back to the formula sheet, right? The rule that we're gonna use, is this one here. Remember this formula sheet. So here we have 2 independent random samples from normal, and we are assuming that the variances are equal and are not. In this case, the rule for testing this versus this is this. So I'm going to use this rejection rule to do part 2, right? All right, so let me first write down. So in this case, the rejection rule for H0 is as follows. Right, this is the rejection rule. Right, let me put this in a box, right, and call this star. Okay, so I'm gonna, as usual, I'm gonna compute the left-hand side and the right-hand side. All right, to compute the left-hand side, I need this guy here. Remember, SP squared, I don't know whether you guys remember, is the pooled sample variance, which I mentioned to you before in the class, and is defined by the following formula. Excuse me. This, if you remember, this is the formula for SP squared. It's known as the pooled sample variance, right? Now to compute this, we know that M is We know from M is what was M? Trying to remember. 33. Yeah, M was 33. So this is 33 take away 1 times Sx squared, which is, trying to read the question just a minute. Sx squared was what? 16.36. N was 37, so it's 37 take away 1 times Sy squared, which is 18.92, divided by M plus N minus 2, which is 33 plus 37 take away 2. Now, if you compute this, you will get this to be equal to 17.715. So this is your spooled sample variance. So this implies that the left-hand side of star is equal to X bar. X bar is, we know from earlier, that is 28.2. Y bar is 30.7, right? Divided by SB squared, which is, sorry, this should be, just a minute, there's something fishy here, something. Okay, it's okay. This is 17.715 times 1 over M is 1 over 33, 1 over N is 37, right? Okay, now if you compute this using a calculator, this will be equal to 2.481. All right, so that's the left-hand side of star. The right-hand side of star is equal to, I'm going to use this, right, which is T at 33 plus 37 take away 2. Alpha is 0.05, which is, right. All right, now you can argue that because this number is large, you can approximate this by the Z percentile, but you have a table for reading T anyway. So, I mean, this is not as complicated, as complicated as in part 1, where we had this A, which was very, very complicated expression. And this is very simple to read, actually. This is 33 plus 37 minus 2 is 68, right? And you can directly, I mean, from the T table, you can directly read 68 and this, right? And if you do that, you will get this to be 1.995, right? Okay, so there's no need here. There's no need here to approximate this by a Z percentile, because this is 68 is very easy to read from the T table, right? Okay. So this is the left-hand side and this is the right-hand side. Clearly, 2.481 is greater than 1.995. So the conclusion is that there is evidence to reject the null hypothesis, right? All right, so I've shown, so this question 3 is slightly different from the 2 previous examples that we did, because in the first part of question 3, we had the case where the population variances are not equal, right, and unknown. And in the second part of question 3, we had the case where the population variances are equal and unknown, right? So we had to use 2 different rules. We had to use 2 different rejection rules for the 2 different parts of this question number 3, right? Are you okay, guys, or any questions on this? Hello, guys, talk to me, please. Are you okay or not? If you're not okay, please feel free to say so. I'm happy to go over as many times as you want. All right. Okay. Sorry, it seems I have run out of time. So I've done the first three, but unfortunately I don't have the time to do 4 or 5. But I will post the full solutions to all 5 questions on Thursday of this week. If you go to the website, you'll be able to see the typed solutions, the handwritten solutions, and the video solutions for all 5 questions. Right. All right, guys. Have a great morning or afternoon wherever you are. And as I said in my email to you, any questions about the exam or anything to do with the course, please feel free to contact me 24/7 by email, Skype, Zoom, or phone. And also, I'm also happy to meet you in person if you are in Manchester. All right, guys. So have a great day, and please take care of yourself, whatever you're doing. And I'll talk to you shortly. Okay. All right. Bye, guys. There is a tutorial now from 11 to 12, so you may want to hang. If you want to listen to that, please hang around. Guys, good morning or good afternoon. Uh, welcome. Um, um, all right, guys. So this is week 12 tutorial. So I'm gonna look at sheet 12. So let me show you the sheet if you haven't seen it before. Um, so this is the tutorial sheet for today, and as you can see, there are 5 questions in the sheet, and I will try to do as many as I can in the time. Right, I will start with question number 1. Right, so here you have you're trying to compare the boiling times, the mean boiling times of 2 different types of equipment. You have type A and type B, right? And you're given the sample sizes and the sample means, right, of the boiling times. And you're also told that the data are normally distributed with the population variance equal to this and this. All right, and we are trying to test at the 5% significance level whether the population means are equal versus mu1 greater than mu2, right? Okay. All right, now to do this question, I mean, all the questions in this tutorial sheet are based on two sample test of hypothesis. Now, let me take you through what I did about 2 weeks ago. So this is the sheet one I gave you 2 weeks ago. In this sheet, we are assuming that you have two different random samples from two different normal populations, right? And we are assuming that the population variances are known. And in this case, the rejection rules for the three different hypotheses are this one, and this one, right? Okay. Okay. And that's the first thing I did about 2 weeks ago, you may recall. The second thing I did, the second set of rules I gave you are for this situation where you have two independent random samples from two different normal populations, but their variances are equal and unknown. And in this case, the rejection rules take these three different forms, right? Okay. Right, that's the second case I considered. The third case I considered 2 weeks ago is the most general case where you have two independent random samples from two different normal populations, and the variances are not equal and unknown, right? And in this case, the rejection rules are these three, right? And this is case 3. And case 4 I did. The case 4 I did 2 weeks ago is where you have two independent random samples from two different Bernoulli populations, and these two are the population proportions. And these are the test of hypothesis, and these are the rejection rules, right? So these are the four things I talked about with respect to test two sample tests of hypothesis. Now, in this question, in the question 1, you have two different samples from two different populations. These are the sample sizes. These are the sample means, and you're told that the population variances sigma 1 squared and sigma 2 squared are known and equal to this and this, right? So the rule that you need to use for testing this versus this corresponds to case 1, because we are assuming that the population variances are known, right? And we are trying to test whether the means are equal versus this being greater than this. So the rejection rule is clearly this one. This is the rejection rule that we need to use in order to answer question 1, part 1, right? Is that clear to all of you guys? I mean, in the most important, the most difficult part in answering a question on test of hypothesis is to find the correct rejection rule. But if you did not get that correct, then everything you do will be wrong, right? So it's really, really important that you figure out the correct rejection rule. So for question 1, this is the rule that we're going to use, right? Okay. Let me know if you did not follow what I said. Okay. All right, guys. Please do. Right. So this is question 1, part 1, right? So the rejection rule that we're going to use is as follows. Right, so this is the rejection rule, right? And it's really, as I said, I mean, it's very, very important that you get this correct before you start doing the question, right? Let me call this star. Now I'm going to compute the left and the right hand side, but before I do that, let me write down what is given to us, right? So according to the question gives you the following. It gives you m equal to 10, n equal to 12, right? And it gives you x bar equal to 11.4, y bar equal to 9.9. It gives you sigma x squared is equal to 6.25, and sigma y squared is equal to 9, right? And it tells you that alpha, the level of significance, is 0.05. Right, so these are the data that's given to you guys, right? So what I'm going to do is I'm going to input the data into the left and the right hand side and compute them. All right, so let's start with the left hand side. Right, so your x bar is all right. And if you compute this using a calculator, this is what you will get. Right? All right, guys. Now the right hand side, alpha is 0.05, so you get 0.95. And if you read this off the normal table, you will get this to be 1.645. So this is the right hand side and this is the left hand side. Clearly this is not greater than 1.645. So the conclusion is that we cannot reject the null hypothesis. All right. In other words, we say there's no evidence to reject the null hypothesis. Right. Okay, guys. All right. So that is this clear to you or no? Before I do the second part. Hello, guys. Talk to me, please. Are you okay with this? Yeah. Okay. Thank you. Okay. All right. So the second part I'm going to do. So I've done the first part of question 1. Second part is, what is the probability that the test will correctly reject H0 if μ1 minus μ2 is equal to 2? All right. So let's see how we can do this. So this is question 1, part 2. So we are looking for the probability of rejecting the null hypothesis when the difference in the population means is equal to 2. All right. So now if you go back to part 1, this is the rule for rejecting the null hypothesis. All right. So let me write it down. Let me write it down. So it's gonna be 6 sigma x squared. Sorry, let me write it down in full, and I will put in the numbers. Okay. All right. So this will be equal to. Now let me put in the numbers. So if you put in the numbers, we have sigma x squared is what was it? It's 6.25. M was 10. Sigma y squared was 9 divided by 12. And this guy was I think it was 1.645, right? 1.645. Okay. All right, guys. All right. The next thing I'm gonna do a trick that I will let you know why I'm doing this in a second. But let me apply the trick. I'm gonna take away 2 from this and add 2. Can you show part 1 again, Vincent? Yeah. Can you see this, Vincent? Hello, are you okay? Okay. Yeah, I mean, I will. You can see the video again in the YouTube. I will post the video in YouTube right after the class, so you'll be able to see it. Okay. Okay. Okay, guys. All right. All right. Now, what I'm going to do is I'm going to take this guy here, this number 2, to the right-hand side of the inequality. Right. So this will become okay, given that. Okay. All right. Now let me ask you, what do you know about this? What can you say about this, given that the population means, the difference in population means is equal to 2? What can you say about this? Do you remember something we did before? Hello, guys, talk to me. Yeah, thank you. Yeah, thank you, Mikhail. Yeah, I mean, if you don't remember, I will write it down one more time. I mean, if you have a random sample of size n1, which IID from normal with parameters, say, mu1 and sigma1 squared, right? And another random sample of size n2, which is also IID from a normal with parameters this, right? And if you suppose that these two are independent of each other, in other words, they are independent random samples, right? Then the following result is true. I think I actually proved this result in one of the videos. In one of the videos I did, I showed you how to prove this. But obviously, I don't expect you to know the proof for the exam or anything. But you can, if you can remember this, that's good for you. Anyway, I proved that this expression here must have the standard normal distribution, right? So this is something that I showed you in a previous video, in one of the videos earlier. All right. So using this result, right? Using this result, we can argue that conditional on this, because this what you have here is exactly of this form, right? This must have a standard normal distribution, right? All right, so that's what I'm going to say. Using this result, we can write this guy here as the probability that a standard normal variable is greater than 1.645, take away all right. Okay, guys, so once again, we don't need the conditioning anymore because we have used the conditioning to argue that this has the standard normal, right? So we don't need it anymore, right? Okay, and this probability can be written as 1 minus 5. Remember, 5 is the CDF of the standard normal at 1.645, take away okay. Now, if you read this off the table for the normal distribution or using R, this is what you will get. You will get this to be equal to 0.52. All right, guys, so that completes question 1, part 2. Right, are you have any questions on this, guys? I mean, please feel free if you have questions. I mean, I don't mean to discourage you. I mean, are you guys okay with this or not? Hello. Thank you. All right. All right. So we're done with question 1. So let's move on to the next question here. So here we have two different types of tires or something. Yeah. So you have type A and type B, right? And you are told that the sample sizes are both equal to 25, and the sample means are these, and they both have a normal distribution with the common variance equal to 1.742, right? And the first part is asking you to do a 5% test, whether there's a difference in the mean for the types A and B, right? All right, so in this question, once again, you have to read the question very, very carefully. It says that the variance is equal to 1.742, right? Which means that the variance is known, right? The variance for the two populations is known and equal. So once again, the rule that we need to use corresponds to case 1, because this is the only case where the variances are known, right? Yeah, and in this question, they're equal. Besides being known, they are also equal. Now, in the first part, we are trying to test whether there's a difference in the mean or not. So the rejection rule that we should look for is this one. So because this is the equality versus not equality, right? So equal or not equal. So this is the rule that we need to use, right? Okay, so let me write that down, what I just said, all right? I mean, if it's not clear, please let me know. So question 2, part 1. So the rule that we need to use for this is as follows. Right? So let me put this once again. Let me start, right? Okay, now let me write down the data that's given to us. We are told that M is 25 and N is also 25, right? And we are also told that excuse me, you're also told that X bar is equal to 10.24, Y bar is equal to 9.76. And we are told that sigma squared, which is so the variances, in other words, sigma x squared is equal to sigma y squared is equal to 1.742. And we are also told that alpha is 5%. So this is all the data that's given to us, right? So using this data that I'm gonna compute the left and the right hand sides. So let's start with the left hand side. Okay. So it's gonna be X bar, which is 10.24. Yeah. Right now, if you work this out using a calculator, you will get the following. You will get it to be 1.286, right? All right. That's the left-hand side. The right-hand side of star is alpha is 0.05, so that's gonna be 0.975, right? And if you compute this using the normal table, this will be 1.96. All right, so this is the left and this is the right. Clearly, the left is not greater than the right. So we cannot reject the null hypothesis. So the conclusion is that there's no evidence against H0. Right. Okay. Is it clear to all of you now? Everybody stop me, please. Are you guys okay with this before I do the next part? Hello. Thank you. All right, so let's move to the second part of question 2, which is asking you what is the probability that the test will incorrectly fail to reject H0 if the difference in means is 1, right? So you have to read the question very carefully. It says will incorrectly fail to reject the null hypothesis, which means that you accept the null hypothesis when the true difference is equal to 1, right? So the probability that you're looking for is the following. You're looking for question 2, part 2. You're looking for the probability of accepting the null hypothesis when the difference in the population means is equal to 1. Okay. All right. Now, all right. Let's go to part 1. This is the rule for rejecting the null hypothesis. So the rule for accepting the null hypothesis will be the reverse of this rule, right? So instead of greater than, you're going to have less than or equal to, right? Yeah, you follow what I've done. Okay. All right. Okay, now I'm going to put in the numbers that we have. All right, sigma x squared we know is 1.742. M is 25. Yeah, and the same thing here. We know alpha is 5%, so this guy is 1.96. Okay, you guys with me? Yeah, it is type 2 error, Mikhail, you're right, yeah. It is type 2 error, yeah. So this guy you can write as, you can write, because these two numbers are the same, so it's 2 times 1.742 divided by 25, less than or equal to 1.96. Okay. All right. The next thing I'm going to do is the following. I think I mentioned this before. If you have something like, okay, if you have a number z, the absolute value less than or equal to a, then you can. It's the same as saying that. Do you remember this or not? This is a result I talked about some time ago. I mean, you should know this from your math courses, not from, it's not statistics. I mean, this is, yeah, right. So I'm going to use this result. I'm going to use this, all right, to write down the above as follows. Okay, you see what I've done? I have taken and get rid of the absolute sign using this fact. Okay. All right. The next thing I'm going to do is the trick that I applied in question 1. You may recall. Now, because the true difference between the population means is 1, I'm going to apply the following trick. Right. So I'm going to take away from this 1. And because I have done this, I need to add a 1, right? Okay. All right. Now, in the next step, I'm going to take this guy here, the third term in the numerator, to either side of the inequalities, to the left and to the right. Okay. So if you do that, this is what you will get. You will get so this is what you get on the left, less than or equal to x bar minus y bar minus 1. All right, and on the right hand side, you will get 1.96. Okay. Right. Okay. Now going I'm going to use the same argument I used in the previous question. Conditional on the differences in population means equal to 1. This must have the standard normal distribution because of what I said a few minutes ago. Remember, excuse me. Remember this. This is the result I talked about in question 1, right? So using this result, we can see that this guy here, this guy here must have, that is, I mean, the thing in the box must have the standard normal distribution, right? Okay. Okay. So this becomes the probability that minus excuse me. I'm trying to squeeze 2 pages in one shot. Just a minute. Just give me a sec, guys. Minus 1. Okay. Less than or equal to 1.96. Take away all right, so this is what you will get. All right, because once again the conditioning is not needed anymore because we have used the conditioning to argue that this has the standard normal. All right, are you with me so far? Yeah. Okay, finally, or not finally yet, but you can rewrite this as the difference of the phi's. Remember, phi is the CDF of the standard normal. So this is phi at this. All right, this is phi at this. Take away phi at right, and if you work this out using the normal table, the answer that you will get is equal to 0.24. All right, so that's the answer to part 2 of question 2. Are you guys okay with it? It seems like a lot of calculations, but if you practice enough questions, you should be okay with this. I mean, as I said, the course website contains plenty of questions you can practice on. All right, are you okay with this, guys, or no? If it's not okay, please let me know. All right, so we're done with question 2 finally. Okay. All right, now let's move on to question 3, which is this one. So you have 2 different drugs, A and drug B. Drug A is given to 33 people. Drug B is given to 37 people, right? And go to the next page. So these are the data that you have. So these are the number of people that the drugs are given to. These are the sample means of the absorption times, I guess, for the 2 drugs. And these are the sample variances, right? And we want to test at the 5% level whether there's a difference in the mean times to absorption for the 2 drugs, A and B. There are 2 parts. The first part is to assume that the variances are not equal. And the second part is to assume that the variances are equal, right? All right, now you should read this question very carefully, because the question says explicitly that the sample variances are this and this, which means automatically, which means that the population variances are not known, right? Okay, so in this question, you cannot use any of these rejection rules, right? Because here we are assuming that the population variances are known. So none of these can be used. And for the first part, we are assuming that the population variances are not equal. So again, none of these can be used, because here we are assuming that this is case 2. We are assuming that the variances are equal. So none of these rules can be used. Now go to case 3. This is case 3, where the population variances are assumed to be unknown, and these are the 3 rejection rules. So in order to test whether there is a difference in the mean times or not, right? The rejection rule that we need to use has to be this one, right? Because this corresponds to equality versus not equality, right? So this is the rejection rule that we need to use, because this corresponds to case 3, where the variances are not equal and unknown, right? All right, so that's the first thing you must figure out. I mean, as I said before, figuring out the rejection rule is the most important part of any question on test of hypothesis, right? Because if you get that wrong, then you're in trouble, right? Okay, so let me write it down. So this is question 3, part 1. So we're gonna reject H0 if the following is true. So let me put this in a big box, right? And call this star once again. Right, now, before I start the question, let me write down what's given to us. We are told that M is 33. We are told that N is 37. We are told X bar is 28.2. Y bar is 30.7. Sx squared is 16.36. Sy squared is 18.92. And we are told that alpha is 5%, so 0.05. So these are all the data that's given to us, right? So we can now compute the left and the right hand sides. Okay. So let's start with the left hand side. Right. So this is gonna be, sorry, excuse me. You cannot see me. I know. It's gonna be 28.2, take away 30.7 divided by 16.36 divided by 33 plus 18.92 divided by 37, right? Right now, if you compute this using a calculator, this will be equal to 1.286. So this is the left hand side, right? Now the right hand side of star, right, it's going to be TA. Well, alpha is 5%, so 1 minus alpha by 2 is this, right? Okay, now A, if you recall from 2 weeks ago, the formula for A is really complicated. This is the formula for A. As you can see, this is a really complicated expression. I mean, in an exam, this will take you ages to compute. So it's best not to use this formula, or best to try to find another way, right? All right. So what I'm saying by that is that it's best to find an approximation for this. Now, if you look at the sample sizes, you have 33 and 37, right? And 33 and 37 are large sample sizes in statistics, because I think I mentioned this before, anything above 25 in statistics can be considered large. So certainly these two sample sizes are large sample sizes, right? So therefore, in such cases, you can approximate the t percentile by the z percentile. I think I mentioned this before, that the t distribution approaches the z distribution, the normal, when the degree of freedom approaches infinity, right? So that's the argument, that because these two are large enough, right, you can approximate this by this. And this is easy to read, which is, I'm sure you know, this is 1.96, right? Okay, so this is the left and this is the right. And clearly, once again, the left is not greater than the right, okay? So once again, the conclusion is that there is no evidence. Just a minute. Sorry, did I do this right? I think I made a mistake. Just a minute. I think I messed it up. Just a minute, guys. Yeah, this is one. Yeah, this is not 1.286. This is actually equal to 2.49. 2.49, guys. I apologize for this. So the left hand side is 2.49. The right hand side is 1.96. Vincent, yes, something is large, Vincent, if it's greater than 25. So 33 and 37 are large, Vincent. All right. So you can, for large sample sizes, as I mentioned before, the t percentile can be approximated by the z percentile. All right. So that's what I have used, and this is equal to 1.96 from the normal table. So, all right, since 2.49 is greater than 1.96, there is evidence to reject the null hypothesis. Right. Okay. All right, guys, are you okay with this or no? So the trick, I mean, the trick I have used here, guys, is the following, that because the right-hand side involves this, and A is a messy expression, you don't want to deal with the messy expression, especially in an exam time, especially in an exam, right? So it's best to approximate this by this. You can do that because these two sample sizes are large, and they are greater than 25, right? Okay, so this is what you get in the right hand side, and this is the left hand side. So there is evidence to reject the null hypothesis, right? Okay, all right. So that's only the first part of question 3. Now the second part of question 3 is asking you to do the same thing, assuming that the variances are equal. So in this case, you need to go back to the formula sheet. You need to go to the formula sheet, and the rejection rule that you need to use here is this one. This is case number 2, where you have the variances are equal and unknown. So in order to test equality versus inequality, the rejection rule is this. All right. So in order to, so let me write it down. So in order to do question 3 part 2, right? The the rejection rule that we're going to use is corresponds to case 2, because we are assuming that the population variances are equal but unknown, right? All right. So let's put this in a big box, right? So once again, what you need to do is to compute the left and the right hand sides, right? To compute the left hand side, you need the SP squared. SP squared, I don't know whether you guys recall, is known as the pooled sample variance and is given by the following formula. If you look back in the video or the notes, you will see this formula for the SP squared, right? And if you put in the numbers, for M and the N and the various other things, this is what you will get. So this is going to be, M is what? M is 33. So it's 33 minus 1 times 16.36. N was 37. 37 minus 1, excuse me. You cannot approximate chi-squared to Z. No, only T you can approximate to Z. There's no such result approximating chi-squared percentile to Z. That was one of the questions that are being asked. All right. All right. So this is the formula for the pooled sample variance, and if you compute this, this will be 17.715, right? Okay, and therefore the left-hand side of star is gonna be equal to the following: 28.2 take away 30.7 divided by SP squared, which is 17.715 times 1 over M, which is 33, plus 1 over N, which is 37, right? And if you work this out using a calculator, you will get 2.481, right? Now, the right-hand side of star is this guy here, right? So it's going to be T, M is 33 plus N is 37, take away 2, 0.975, right? Now, you can argue again that because this is a large number, you can approximate this by the Z percentile. But there's no need to do that here, because this is, you can easily read this, because this is simply 68, right? And you can, using the T table, you can easily read 68 and this from the T table. So there's no need actually to approximate this by the Z percentile. You follow what I'm saying? In part 1, we did say so. We did do the approximation because the expression for A was very, very complicated. But in this case, it's not. 68 is 68, right? It's very easy to read, right? And this is what you will get. Okay, so this is the right-hand side, and this is the left-hand side, right? All right, and since this is greater than this, again, the conclusion is that there is evidence to reject the null hypothesis. All right. Okay, guys, so that completes question number 3. Are you have questions on this or not? Are you okay with this or not? Okay. If you're not okay, it's okay. I mean, I'm happy to answer questions you have. All right, guys. So unfortunately, I was only able to do the first 3 questions, question 4 and question 5. You will be able to see the solutions on the course website on Thursday of this week for all the 5 questions, right? Including 4 and 5, which I was not able to do today. Sorry about it. Okay. And so you will see the solutions in 3 different formats: the typed solutions, the video solutions, and also the handwritten solutions, right? All right, have a great morning or afternoon wherever you are. And once again, as I said before, if you have any questions you guys have, please feel free to contact me 24/7 by email, Skype, Zoom, or phone. Okay. I'm here. I'm here throughout the summer, so just feel free to contact me anything about anything. Okay. Okay, guys, take care of yourself. Right. I'll see you. I'll talk to you shortly.